Still. Okay. Oops. Okay, good afternoon, everyone. Welcome to CS 61 learning probabilistic learning or probabilistic modeling class. This is the very first lecture in this semester. So very appreciate that you registered for this course. And today we're gonna talk about, probably this lecture and next lecture, we're gonna talk about our course plan, what kind of topic we're gonna discuss, and also course policy. Okay, so before that, let me briefly introduce myself. So my name is Shandian Z. Well, this family name is kind of difficult to pronounce, so you can call me Dr. Z or Professor Z or Shandian, whatever you want. And I'm assistant professor at School of Computing at University of Utah. So my research area focuses on this probabilistic machine learning. So I'm very excited to be able to teach what I'm studying on for tens of years. So very excited on that. So my research topic includes, but not limited to, like Bayes nonparametrics, Bayes in deep learning, probabilistic graphic models, and large-scale learning system, high-order structure factorization, embedding learning, etc. And meanwhile, I'm actively applying machine learning techniques to a variety of applications like collaborative filtering, like physics simulation, like brain imaging, data analysis, like blood transfusion prediction, all kinds of stuff. So I personally very fascinated in machine learning, especially in my own area, because it provides, as we'll discuss later, it provides an excellent framework to integrate prior knowledge and data information, and also it allows us to do the uncertainty quantification in a very rigorous and principled approach. But of course, there are many challenges in this area. That's why we're doing probabilistic learning research, right? It hasn't been like mature enough yet. Okay, so the outline of today's lecture. Right? So we're gonna first briefly, very generally, explain what is probabilistic machine learning. Maybe you have how many of you have taken the machine learning class before? Oh, nice. How many of you have taken my class? Oh, okay. That's why I feel why so many faces are familiar. Okay, so first we're gonna talk about the difference between, the ordinary machine learning and probabilistic machine learning. Right? What's the key difference and why? Why should we emphasize on probabilistic perspective. And then we'll talk about the benefit or the advantage of conducting probabilistic learning, right? Of course, I mean, there's no free lunch. If you have some kind of benefits in one aspect, you're going to face a bunch of challenges from the other side. So we're going to talk about what is the challenges, right? So actually, the frontier research is always trying to address those challenges. And then we're going to talk about the course requirements and policies. So we're going to talk about how do we design homework assignments and how do we design projects, and also discuss later. We don't have any midterm exam or a final exam. So I don't think that is a good way to examine if you're really into this class. Right? So what do we expect that you're trying, you're doing good in the homework assignments and projects. That's enough for you to know everything about, not know everything, but know good about probabilistic learning, right? And then we're going to talk about the basic knowledge review before we get into a variety of probabilistic learning concepts, a variety of prior distributions, conjugate distributions, and different models. We're going to quickly review some basic knowledge, but this is not going to be a comprehensive review because this is an advanced class. It's not some like class tell you how to do matrix multiplication or take the derivatives or apply the chain rule. We assume that you're familiar with that. Right? Later we'll talk about some prerequisite requirement, or we assume you should be familiar with that. If you don't feel comfortable with those, I'll suggest to seriously consider if you're going to take this class or not. Okay. So this is a sentence copied from my machine learning class, right? Some kind of formal definition of machine learning. Oh, by the way, if you have any question or you have any concern, just interrupt me at any time. Right? This is a relatively small class, a small lecture room. So just raise your hand and interrupt me. Right? So what is machine learning? Here, I appreciate one kind of formal definition of machine learning given by Professor Tom Michel from CMU. And he said that a computer program is said to learn from some experience E, which is usually referred to as training data, for some class of tasks T, right? So such tasks can be like image classification, right? Can be voice recognition, can be autonomous driving, right? A lot of tasks, right? And also we got some performance measure P, right? Once you got some thing or some machine, you got some program, right? You want to apply it to do some task, you need some measurement telling you if it is doing good or bad. Right? And once we have this training data, type of tasks, and a performance measure, if this program, we can see that its performance in this task T measured by P improves with the experience E. Then we call this program can do learning. Right? It's kind of similar to human learning behavior, right? So if you're kind of like has no knowledge about machine learning or whatever, what else, right? So now I gave you a bunch of knowledge, right? So our knowledge or our training data will be a series of lectures, slides, and including project assignments and homework assignments. And through dealing with those lecture slides, lecture videos, and homework assignments, and which we refer to as a training procedure, right? Now, giving you a specific machine learning problem, you can formulate a model, you can implement some algorithm, and you can develop own algorithm to solve that. So machine learning is defined in a very similar way to human learning. So nowadays, people have heard like buzzwords called artificial intelligence like every day, right? So everything, and the whole country, or the whole, Earth is kind of fascinated with artificial intelligence. Right? Artificial intelligence is kind of like a critical techniques, and even brings in serious competition among different countries. Right? So, but if you have taken some artificial intelligence tutorial course or introductory course before, you might have known that artificial intelligence has a long history. Right? This concept was proposed about 80 years ago. Yeah, it's about 80 years ago. Since it's being long, right? It was defined by some like pioneer in this area who has already passed away, right? And the development of artificial intelligence has going through several like waves, like up and down, up and down. This is the third wave. So at the beginning, people are very optimistic about artificial intelligence, and they claim that, okay, they're going to build up a thinking machine, real thinking machine in 6 months. Yeah, this is the famous artificial intelligence conference at Dartmouth, right? But after that, people found that this problem is really, really difficult. Really difficult. It's more than what they thought, right? So and then after like a few like 20 years development, and then all the fundings, all the investment stop, right? People becomes quite pessimistic, right? And then later like with the development of new techniques like artificial neural networks, like support vector machines, all kinds of stuff. So they kind of like research, right? And then going down. And now this is third time research. And I'm kind of still a bit pessimistic about artificial intelligence, in that I don't believe strong AI and like real human-like AI will become true in the foreseen future. I don't think so. But there are indeed fancy applications that artificial intelligence has shown working as good or even better than human beings. Right? For example, the Go play game, right? Playing Go game, right? So I have brought this example to my machine learning class, but here I just want to repeat here to emphasize my surprise when I first heard about this, right? Because the Go game is known to be the most difficult, deterministic game, chess game, right? Why? Because its state space is too large, right? If you want to use brute force search approach, like imagine you got a computer, you got two computer programs, or two robots, right? They're playing Go game with each other, right? So if you're very powerful, you're like a god, you have infinite amount of computational resources and time. You can imagine your robots can record every possible playing steps, right, until the end of the game. You store all of them, and then you just build this huge databases, right? And then when you play with human beings, right, when every step you can search it in your big database, and then going to which step in the next you're gonna win the game at the end, right? Yeah, this is kind of like ideal, but in practice that won't be feasible, because if you really compute the total number of games you can play, that's kind of like a huge number, huge number. I cannot memorize the magnitude, but I can tell you it's much larger than the total number of atoms in the universe. So it's not possible. And at the beginning, people have developed several other computer players for other games, like other chess games, right? They kind of like Deep Blue, developed by IBM. But even they have their computer players have beaten the world champion in 1997. At that time, people are still kind of like pessimistic about Go player, and many scientists or engineers, researchers claim that it won't be able to say like a reasonable robot Go player in their life, right? But just after 20 years, right? We know that based on deep neural nets, based on reinforcement learning, people have developed this AlphaGo, right? It has beaten the world champion, right? Who's now Chinese, right? Previously it's Japanese and then Korean, and now switched to Chinese. But anyway, no human beings right now can win computer games, computer players. And in addition to this fancy, cool game, right? Even in the daily lives, machine learning has penetrated in every aspect of our life, right? Like recommendation, like in Amazon, like in eBay, or whatever else online stores. Some kind of annoying recommendations are always with you. They are done by machine learning algorithms. So don't complain too much, because this is their way to earn money. So every time they recommend you some kind of product, even like 1% of you guys have clicked that product, they're going to earn money from the advertisers, right? And imagine you have 1 billion users or customers, right? And even 1% of people have clicked that advertisements and purchase something, you're going to earn a lot every day, right? So that's why like those online advertising system or online recommendation system have recruited like most brilliant people, like in Facebook, like in Google, right? And also the translation, automatic translation, spam filtering, and also autonomous driving. So right now, if you have a autonomous driving, it's kind of like very common in cars, right? Cars and vehicles. I think the most famous example is Tesla, and also Google Waymo. If you stopped by the Phoenix City in Arizona, Google has provided some like autonomous bus. There's no driver there. You can take on a bus, then they're gonna send you to some designated places. So that's very cool, right? If you take a if you're a Tesla owner, wow, you can really experience the autonomous driving. Right? I have a friend who lived in LA, and he tried the Tesla. He told me that Tesla's driving is kind of like it's a bit like a crazy human beings, because they're trying to approach the car in the front very close. Right? I'm kind of like scary about that. I don't want my student my car to be followed very closely, right? Or I don't want to get close to the car in my front, right? But this is how they do the autonomous driving. I'm just I kind of like highly recommend you to look at some like recent autonomous driving videos released by Tesla. It's really impressive. You can see that they leverage some like image recognition techniques. When they drive that, they can tag all possible marks, people, objects during the driving process, and also they can read the lines very accurately. So it's very impressive, and also their techniques is quickly improving. So I believe that in someday the autonomous driving, I mean the 3-level autonomous driving, the real autonomous driving, will become the reality. At that time, I never need to worry about I'm going to be sleepy when I drive on the highway, right? I'm always easy to get sleepy when driving on highways, right? Okay, but anyway, to summarize, machine learning is everywhere, right? Not in those fancy, cool applications appear in the news, but also in your daily lives, no matter if you realize it or not, right? So spam email filtering and tag people's in the photos and movie rating recommendation of the movies, and also a bunch of people in Wall Street, they develop their models to predict stock prices and earn money. So this is like hedge fund, right? So I got my one of my academic brothers who recently joined a millionaire hedge fund. It's very famous hedge fund, and he refused to tell me, disclose any details about what he's doing, because it's highly it's a top secret. They won't write any piece of paper, but he just asked, are you doing some and curiously, I mean, he just asked me, what are you doing right now? What kind of research are you doing? Are you doing some ensemble learning plus reinforcement learning, something like that? I'm saying, okay, he might do this to combine those models, you know, to earn a lot of money. So handwritten recognition. This is a kind of a long time. The handwritten recognition, this thing has already been applied in post office for a long time, like I think for decades, because we send a letter. Right now, people won't recognize. We won't look at the postcode by themselves. They always throw it to some machines, only leaving those very hard to recognize ones to human beings. And online advertisements and translation, right? Language translation. So I've seen the whole evolution of the machine translation techniques. I mean, when I was in my undergrad school, I've seen the first release, the first version or first release of Google's machine translation. At that time, I mean, the quality is really bad, and kind of like people at that time we were kind of like tested with different sentences and mock it, right? But nowadays it's totally different, right? It's totally different, and in many cases I can just paste a large paragraphs of English into that and just read Chinese. By the way, I'm from China, so I'm not expert in looking at English things or other things, or sometimes you can copy, you know, some YouTube video under there are comments from different languages, right? Just paste them into Google Translation, and you get to know their meanings. This is very cool, right? And autonomous driving, and also medicine. Yeah, in the medicine service, like how do you use machine learning techniques to help you diagnose disease? So so this area is also progressing very fast, because it's like people look at your X-ray pictures or scans, right? So it's very hard to diagnose if there are some tumors there. So it's only highly experienced doctors can do that. But right now, by leveraging machine learning techniques, especially like deep learning techniques, they can achieve even better diagnosis accuracy than highly experienced doctors. So I think this is really a promising direction, because we're gonna reduce the medical expense, right? But of course, there are many controversial things there, like how do you make up laws, right? To address law problems. Okay, so we know that machine learning is a horsepower of artificial intelligence, and has been successful in many areas, right? And but this class is talking about the probabilistic learning, right? A small branch or another branch of machine learning. So what is probabilistic learning, right? So can we use one sentence to summarize probabilistic learning? Probabilistic learning is a branch of machine learning that uses probabilistic principles, or in other words, Bayesian principles, to model for model design and algorithm development. So basically, if your machine learning techniques follows a probabilistic framework of principles in both modeling and computation, then we call it probabilistic model. So it's kind of very general definition, and many algorithms and and techniques can be categorized into this direction. Right? So why probabilistic learning? Right? So of course, there is probabilistic learning. There is a non-probabilistic learning. Right? What's the benefit of doing probabilistic learning? What is benefit of doing learning in a probabilistic way? Right? So here I just want to share my feeling or my ideas. Right? So probabilistic learning actually provides a rigorous and a convenience framework to integrate your existing knowledge and new knowledge. This is kind of very common in human learning behavior. So you know that when we learn something, we're not always from scratch, right? So we know we learn, we try to study machine learning, but you have some prior knowledge about that, right? Even including your basic knowledge like statistics, like calculus, like linear algebra, all those things. Right? You're not like total empty in your brain, right? You always have something in your mind. Right? And then after you look at books, right? You do some practices or you implement something, you debug something, right? You're actually absorbing information or knowledge from data. Right? And then you kind of upgrade yourself internally, right? And after taking this class, perhaps you'll become an expert, right? So this human learning behavior is very natural, right? And correspondingly, in the machine learning area, we want some kind of same framework, right, to enable incremental learning, right? And probabilistic learning gives us such a framework, right, in a very principled way. Right? Our prior knowledge, our prior beliefs, or prior experiences can be encoded in the prior distribution. And then the information extracted in the data in the Bayesian world is expressed as data likelihood. And then how do we conduct the knowledge integration or knowledge upgrade? Right? We're going to combine the prior distribution and data likelihood to compute a posterior distribution. So you can see that we got a prior, we got data likelihood, and then we combine them together to compute this posterior distribution. So if you are able to compute the posterior distribution, you're actually finished the upgrade, right? So, and this computing procedure is just simply the Bayes rule. Sometimes it's also called Bayes inverse rule. So in theory, if you want to compute any posterior distribution, given the data, right, just multiply the prior and the data likelihood, and then divide their integral. This is called a Bayes rule. So overall, Bayesian learning or probabilistic learning provides such a unified and principled mathematical framework, right, in the learning procedure, or to simulate or to imitate human learning behavior, which is kind of important for artificial intelligence. But from the other perspective, this is from a more practical perspective. It provides a rigorous and a convenient framework to quantify the uncertainty. So like, we know that when we do make some predictions, right, want to apply something, right, want to make some predictions, we not only want to know the prediction results, we also want to know the confidence. Right? So we will come to the doctor, right? Doctor said, okay, you have to stop smoking, right, or stop eating too much, otherwise you're gonna have a high chance to get some disease, right, heart disease, asthma, or something like that, right? And the high chance is kind of confidence. Right? So of course, if you can quantify them, like you have a 60% chance to get asthma, 30% chance to get a heart disease, and only leaving 10% chance to stay healthy, you might be warned, and also, you know, you you might feel stressed, and you can start to be on diet or whatever. And also in weather forecast, like we might want to give like prediction, like, okay, I got 30% chance to have rain, right, in the next hour, only 30% chance to be sunny. Then you should prepare some umbrella or just stay at home, whatever. Okay. So uncertain quantification, uncertain reasoning is really important in many decision scenarios, right? Like in online advertising, right? This is another example. Like people are the policy or strategies to show advertisement for different users is like following. So it's not like, okay, I got a prediction model, I got a machine learning model. I tell you, okay, he definitely will like this advertisement I want to show you. Instead, they always calculate some uncertain score. Right? If they are like 100% sure, this guy will like this advertisement, okay, I will display this advertisement. If it is less, then they're gonna kind of like randomly draw another advertisement and to show you, to increase diversity. Why? Because you keep giving some guy a similar type of the same advertisement or similar type of advertisement will easily make people feel tired, right? So now they want to use some uncertain scores to incorporate some diversity, okay, to increase your desire to look at those advertisements. This is also another important application of uncertainty quantification. Right? And because in probabilistic framework, we actually will everything as random variables. Right? We assign a prior distribution over the random variables to express our prior beliefs or knowledge about that. And after we have seen the data, right, we use posterior distributions. We calculate posterior distributions to adjust or recalibrate our confidence or uncertainty. Okay. So this confidence or uncertainties will help us to make decisions or to make some kind of optimal decisions. This is another aspect, advantages of Bayesian learning or probabilistic learning. And also, I want to showcase why uncertainty is so important. Right? This is one crash example of Tesla. I think it's maybe 4 years ago. I guess right now the autonomous driving system of Tesla won't make such mistake, right? But for that accident, both the driver and the autopilot system in our car didn't recognize the big truck here, the white truck here, because they kind of confused this white truck with the white cloud in the sky. So just that car just drives like 70 miles per hour and hate it. It's a tragedy, right? But consider how can we avoid such kind of tragedy? Right? If we are able to give some confidence score, right? Like even I predict, okay, this is kind of like empty, but if my uncertainty, my confidence is low, right? My uncertainty is very large, then I can warn the drivers, right? I can warn the drivers, I'm not sure about this, right? Although I think this might be air, right? This might be empty, right? But I'm not sure about that. Please take a look and touch the wheel, right? And then perhaps that accident won't happen, right? So there are many other such kind of applications in reward. So we have advocated so far. We have advocated quite a few advantages of probabilistic learning. Right? Of course, there's no free lunch. There are also many challenges. Right? So what kind of challenges do we have? So first, although we claim that your prior knowledge, your prior experience should be encoded into some prior distribution, right? But how do you encode them? This is actually an issue, right? So for example, I can use some Gaussian distribution where mean and variance might express my belief, right? But other than that, if my experience is much harder than some Gaussian distribution, much more complex than Gaussian distribution, how do we encode them, right? Like suppose I have some hierarchical structure of all kinds of knowledge, and their organization is quite complex. How do you express them in terms of a valid prior distribution? Like remember, because everything in Bayesian world and in probabilistic world, they have to express in terms of probabilities, right? If you don't have a valid probabilities, you cannot conduct any probabilistic learning. Right? Another thing is that in practice, right, human experience are often expressed as rules, right? Rules of thumb, like rule 1, rule 2, rule 3, right? And those are kind of deterministic rules. How do you convert them into probability distributions? So we'll see that actually in probabilistic learning area, people have come out a lot of very complicated priors. And some kind of priors can cover like infinite cases, right? Not restricted to finite cases, which we call non-parametric prior. Right? And other priors we will see a lot. Right? And this is from modern perspective. Right? From the calculation perspective, probabilistic learning also faces a severe challenge. As we previously mentioned, right? I just mentioned a moment ago, if you want to compute the posterior distribution of anything you're interested in, represented by theta here, right? I mean, you should multiply the prior with the likelihood and divide it by the marginal distribution of the data, right? The marginal distribution is computed by integration of the prior likelihood. Right? This is very simple, right? Very intuitive, but in practice, this thing is nearly always infeasible to compute. The reason is this denominator, right? Denominator, which is integral. This integral is really doesn't have any closed form. It's very hard to calculate. So this is always the problem of a Bayesian learning. So some non-Bayesian learning kind of like criticize that, okay, Bayesian learning is perfect in modeling, but you'll never be able to compute a model. So how do we address this problem? Right? So actually, the whole Bayesian learning or probabilistic learning community, they're always trying to address the competition challenges. Right? So right now, we mainly have 3 strategies to address this challenge. Right? The first one, maybe you have heard them before, is called Markov chain Monte Carlo sampling, right? MC sampling. It's being used, I think, for decades. Right? So, so basically, they're gonna use this joint distribution, like prior plus multiply plus likelihood, to construct the so-called Markov chain. Right? So they're essentially simulating the Markov chain. The Markov chain has a very nice property that it ensures that if the Markov chain achieves the stationary state, then the distribution of the stationary state will exactly follow the posterior distribution. So that's the key idea of a Markov chain Monte Carlo sampling. But the problem is MC is really very slow. We're going to spend a few lectures talking about Markov chain Monte Carlo sampling and introducing the basic ideas and implement those things, and you'll get a sense about that. And another type of method is called variational approximations. So variational approximations in general will be much faster than Markov chain Monte Carlo sampling because it converts the sampling problem into an optimization problem. So you're essentially conducting some optimization instead of performing sampling. That's why it is kind of faster. But the problem is that the variational approximation does not have any unbiased convergence guarantees. So MCMC is something is kind of like guarantee that asymptotically you're gonna converge to a true posterior. But for variational approximations, there is no such guarantee. There is always some gap between the ground truth posterior here, and this is your variational. Right? No matter how optimal your approximation is, there is always some gap. And regarding how large is the gap, nobody knows. Nobody knows. So, so the frontier research of variational approximation is always trying to, okay, I'm gonna make my approximation, I'm gonna decrease this gap as large as possible, while not decreasing the computation speed. A third type of method is called belief propagation or message passing. So this is another way to convert, to avoid the sampling and convert the whole calculation into an optimization problem. But they kind of like represent the whole distribution as a graph, right? Each node in this graph corresponds to a random variable, and those random variables are connected through their drawn distributions, and then you're gonna minimize a kind of so-called energy function based on this graph. So when you minimize this energy function, you'll find some optimal approximation to the posterior. So the problem is the problem of belief propagation is the same as the variational approximation. Okay? So usually you don't have you usually always have some gap of that, but their formulation is totally different because variational approximation usually refer to maximizing some lower bound of the true probability, but belief propagation is doing some kind of minimax optimization. So it's doing is essentially solving some saddle point on that. And it is usually achieved by the so-called fixed point iteration. Okay. So in this course, we're going to cover both the classical and the state-of-the-art techniques to deal with these challenges. So what I want to emphasize is that these challenges are not outdated. They're still there. The only difference is that along with time, right, people have developed more and more advanced tools to address these challenges. But these challenges have never been vanished. Yeah. Okay, any questions so far before we go through the course topic and go through give some overview of this course?
What is the main difference between machine learning and probabilistic? Is probabilistic like a subset?
Yes, exactly. Like there are a variety of other like non-probabilistic machine learning methods. Okay. Machine learning, probabilistic learning is just a small area on that. The machine learning is really big, really big. Yeah. Other questions? Yeah, definitely. Yeah, this is something I'm gonna discuss in a minute about the attendance issue and about the video lecture video recording things. Okay, so we're gonna give an overview of this course to the syllabus. We're gonna spend quite a amount of time on that. Please bear with me because I want to let me just decrease that. I want to jump to the syllabus and go through that so that oops. So first, I want to tell you how to access the course webpage. It's just very easy. You just come to my homepage, and there's a teaching section, and there's a link to pointing to the probabilistic machine learning course. And if you don't know where to find my personal homepage, just search my name on Google. Okay. So let me open the syllabus first. Okay. here's the syllabus. And so this is the course page, right? So we also released the link to the course webpage and syllabus PDF in our Canvas. So if you don't find the if you want to access that, you can access our course webpage through Canvas as well, right? So we have two teaching mentees in this class, and Shikai Fang and Zhimeng Pan. And unfortunately, Shikai right now is stuck in China, and he can he can only provide remote office hours. I think in the next month, right? And when he come back, we can schedule in-person office hours. And Zhimeng can provide. I think he can provide both in-person and office and remote office hours. Right? And here are the schedule of our office hours. So I'm gonna my office hour is scheduled between 2 to 3 p.m. Right now I provide Zoom, but later, because our office hour, the rooms for the office hours has yet been scheduled. So we're still coordinating with the admin. After that fix, we can we'll update the syllabus and also all those in the Canvas. And my office hour is on Wednesday from 2 to 3 p.m. And Shikai will provide 2 office hours. One is on Monday, one is on Friday, from 4 to 5 p.m. So please forgive his late time, because he has to deal with the time difference. There's kind of a 13 hours difference from here and China. Right? This is the earliest time. This is the early morning for him. And Zhimeng will provide office hours on Tuesday and Thursday, and from 1 to 2 p.m. And later he will release the Zoom information first, and later when the tea rooms are ready, and he will show up in the tea office. Okay. So this course, I'm just reading through the sentences, right? So this course introduces basic knowledge of probabilistic modeling and learning, right? Topics cover fundamental concepts of Bayesian statistics, probabilistic graphic models, generalized linear models, approximate inference, right? Including variational inference, message passing, and Markov chain Monte Carlo, and Bayes neural networks, Gaussian processes, and so on, right? So what's the outcome of this class, right? What do you expect, or what do we expect after this class you can do, right? We expect that you will understand the principles and paradigms about probabilistic learning, right? You will be able to explore relevant literature, exploit existing, or even create new probabilistic models for your own research or interest. Right? And you will be well prepared to dive into the cutting edge research in probabilistic machine learning. So here I want to express some warning message, but we'll go to the detail later, right? So this course is highly math intensive. Right? So if you are struggling with linear algebra, calculus, or statistics concepts, don't take this class. That'll be very painful. We're not going to talk about scalars. All the basic objects we're going to talk about are based on vectors or matrices. So, what?
Is there any prerequisite for this course?
Curriculum what? A prerequisite. Yeah, I put prerequisite here. It should be. This should be this prerequisite. Yeah, this prerequisite. You see, they also talk about. I actually don't know the name of the course. This is just the number of these courses. But these courses are about the fundamental math and also some programming requirement. So we're gonna use a lot of math formulas in this class, because without math formula, you don't get to the point what those Bayesian steps mean to, right? And also, we're not gonna operate on numbers. We're operating on vectors and matrices. So it will be very common for me to write down things like matrix multiplications, inversion, and apply their properties to show something, right? So again, if you're not familiar with that, or if you feel uncomfortable with that, please be serious about that. I don't want to feel like being tortured, right? So I want you to learn what you want, right? I don't want you to feel painful on that. But math is not all, right? We also require some programming experience, meaning that you should be confident and comfortable in implementing or programming with math. So this is not programming with other things like you write a web crawler to download some text or doing what else, right? You have to implement some probabilistic models. You have to calculate posterior distributions, and you have to say, okay, if my variance, if my posterior mean look reasonable. So this is quite abstractive. And if you have had some experience in MATLAB and R, that would be very great. Okay? And if you're familiar with Python and NumPy and SciPy programming, and even PyTorch or TensorFlow, that would be even better. Okay? But throughout this class, we're going to have both intensive math and programming. And if you should feel like very comfortable in programming and debugging. Otherwise, that will bring a lot of trouble. So later we'll come to this point later, right? But first, let me introduce what kind of materials we want, right? So we have some major reference textbook for this course. It's a classical book. It's called Pattern Recognition and Machine Learning, written by Christopher Bishop in 2007. It's kind of an old book, but the content is not outdated. It covers a lot of things in this area. And the good thing is that this book is free online, so you can just download it, right? So although the lecture are self-contained, lecture slides are self-contained, it contains all the necessary things you need to do with the homework assignments, the projects, but we still highly recommend you to read through the chapters. We'll list the corresponding chapters in that book. So if you got some time, then please read them. Right? And there can be a few topics which are not covered by the reference book, right? Like the most recent development of a Bayesian model, like Bayesian deep learning, like general adversarial neural nets, the connection between Gaussian processes and the neural networks. Like Gaussian process is essentially an infinite, is an infinite wide neural network. So for that, we're gonna provide some actual reading materials if you're interested. So we also list several books to further extend the depth and breadth of topics we're going to discuss. Right? So this book called Machine Learning, a Probabilistic Perspective, written by Kevin Murphy. He's in Google now. Previously, he's a professor at UBC. And David McKay, he's passed away. Yeah. So this book is very, very classical, connecting information theory, Bayesian inference, and learning. Right? And Larry Wasserman, all of statistics, the CMU professor, written this course. This is very good. You can use them as a reference or dictionary if you want to look at some basic statistics definitions. This is a very good book. And if you want to know some very formal definition of probability, like from merit theory perspective, this is a good book. It's called Probability Path. You know that what is the real definition of random variables. Random variables is not numbers. Random variables are actually mappings or functions. And also probabilistic graphic models. This is a very thick book. Talk about inference techniques, about graphic models in all aspects. Again, I always use this as a reference book. I don't want to read the chapter one by one. It's too thick. Right? Okay, prerequisite. We listed several prerequisite courses, but overall, these prerequisites just to ensure that everyone knows basics of calculus and statistics. Right? And again, this is an advanced class. It's not a entry-level class. So the certain foundations, certain basic knowledge is of great importance. And you're familiar with linear algebra. Here, I highlighted this here. The reason, as I just mentioned, we will do everything use linear algebra. Vectors and vectors, matrices, trees, inversion, determinant, all those things. We're assuming you know that you're not sick of it. Otherwise, we won't be able to progress. Okay. And also have you need to have algorithm design and programming skills. Okay? Again, we're not able to teach you how to debug your code. We're assuming you have such kind of skills. Okay. Any questions so far? Okay. I think next will be very important, like how to get help. Okay. So we actually provide office hours for every weekday. Okay. So I highly encourage you guys to come to the office hours and talk about your problems and ask questions and express your concerns in front of TAs or the instructor, so it can help you, right? So don't try to rush to address to solve the homework problems like 3 hours before deadline. That won't work. So I always encourage you to take advantage of the office hours and seek for help. Right? We're ready to help. And also, we're going to use Canvas discussion group. So feel free to post questions on Canvas. Our TMs will diligently look into those Canvas questions to try to answer them. Okay? So feel free to post questions regarding any questions, okay? Homework assignments and projects, but don't post the answers, okay? And don't share your answers. Okay? And if you found that you post potential homework answers, we have to delete it in a minute. Okay. And again, you can send emails, you can ask questions in Canvas, you can come to the office hours, but we still prefer the in-person office hours or like Zoom office hours, because this kind of face-to-face communication will be much more efficient, right? Much better. Yeah, any question regarding this? Okay, so what kind of course topics we're going to discuss, right? So you can view like we're making a building, right? So we're going to start with those basic concepts. So what are the basic concepts? What are basic items in probabilistic learning? They're all kind of distributions. That's why I request everybody to have such kind of background. You're not sick of like Gaussian distribution, multivariate Gaussian distribution, gamma distribution, Bernoulli distribution, beta distribution, all kinds of stuff. So at the beginning, I mean, at the first a few lectures, we're gonna introduce basic concepts in Bayesian statistics, like what's the definition of probability space, random variables, cumulative density functions, probability density functions, what is expectation, what is variance, what is impedance, and I believe if I'm taking some entry-level statistics class before, you're familiar with that. That's easy. And then we'll introduce a variety of probability distributions, which are very commonly used in probabilistic learning. typically multivariate Gaussian distribution. Right? And student T distribution, beta distribution, gamma distribution, inverse gamma distribution, Dirichlet distribution, and so on. Right? So through learning those distributions, you get a sense, right, for different types of data, what kind of distribution you're going to use, because we're going to leverage those distributions to model data, to extract information from data. Right? You must be very familiar with these distributions. Otherwise, how do you design a model? Right? Then we'll talk about several principles in Bayesian learning, like maximum likelihood estimation, right, MLE, and maximum A posterior estimation, MAP, right? So the first two, right, MAP and MLE, I believe everyone has heard this, right? But in Bayesian learning or in probabilistic learning, we're actually more caring about this predictive distribution. So we'll talk about what is predictive distribution. Right? So actually, maximum MLE and MAP are often viewed like inferior in that they are just point estimations. So we really want to calculate the predictive distributions, namely, given the training data, like given the test point, can you give me the posterior distribution on the test output given the training data? Right? This is called predictive distribution. And how do we calculate that? Right? And then we're going to talk about what is type 2 MLE, right? And actually, most people are where most people are dealing with is type 1 MLE. And then we're going to talk about what is type 2 MLE. And we're talking about the empirical Bayes framework. Like you can partition the parameters you're interested into two parts. One part you only want points estimated, point estimations. The other part you really want some posterior distribution. And how do you conduct that? We're gonna use this framework. It's called empirical Bayes. Right? It's not perfect, but it's often, in many cases, it's just enough useful. Right? And Bayes decision theory, Bayes model selection. This part, we're still not deciding if we're gonna incorporate or not. Right? Non-informative priors, exponential family, and conjugate priors. This is very important. Right? Exponential family plays the key role in Bayesian modeling and inference, and you'll see later. And there are many nice properties of exponential family. So if you have taken a look at our homework 0, there are some problems which seems tricky. But once you know the property of exponential family, it's very easy to compute. And the conjugate price, right? And then those are kind of like bricks to make our building. Right? Once we have these bricks ready, right, we can talk about different types of like those commonly used and classical models. Very useful, right? We're gonna start from the generalized linear models, like Bayesian linear regression, like Bayesian logistic regression, and Bayesian probability regression. Right? So you haven't taken my machine learning class before. We talk about the logistic regression, right? But that logistic regression is different from the Bayes logistic regression. So we see the difference. And multi-class logistic regression and ordinal regression, if you are predicting discrete outputs, and those outputs are ordered, like you want to predict the rank. Right? We should place it as rank 1, 2, 3, 4, right? You know, those labels are ordered, right? So it's not appropriate to just predict a discrete label. You have to consider ordinal order information. Right? How do we build up a probabilistic model doing this, right? And even more general, right? If you want to extend our linear models in the exponential family, what is the general inference framework? Then we'll talk about the probabilistic graphing models, right? This is also a very important. You'll see that graphical representation is kind of widely applicable to all kinds of models, including artificial neural nets. So artificial neural nets is essentially a special type of graphic models, right? So, but we're gonna start with the so-called Bayes networks and the Markov random fields. So the Bayes networks is why Drew Dapur got his tuning award, right? He's kind of his creative work in Bayes networks, telling us how actually create this area of probabilistic graphic models. And then what kind of important properties in probabilistic graphic models? Most important property is the conditional independence. So you see that the benefit of introducing graphic representations is that we can quickly identify which set of variables are independent, which another set of variables, conditional, or third set of variables. We can leverage the structured information to simplify our model estimation and prediction problems. And then we'll talk about the factor graph representations, message passing algorithms. Those are referring to the calculation of posterior distribution, as we just mentioned. So then we'll talk about approximate inference, right? As we just mentioned, right? Calculating the posterior distribution with the Bayes rule is really infeasible, right? We have to seek for some approximate techniques. So we're gonna give some systematic overview about those techniques, from Laplace approximation to variational inference and to expectation propagation, which is essentially special instance of belief propagation or message passing algorithm. And then we're going to talk about the Monte Carlo chain, Markov chain Monte Carlo sampling. Like what is Metropolis Hastings? What is Gibbs sampling? What is Hamiltonian Monte Carlo? And finally, if I have enough time, right, we're gonna talk about how to combine. How is machine learning? How is Bayesian learning or probabilistic learning combined with artificial neural nets? Because right now we know that neural networks are kind of dominant techniques in many applications. Right? So of course we have the counterpart in the Bayesian world called the Bayesian neural networks. Right? How do we conduct inference with Bayesian neural networks? Right? We're going to introduce the so-called Bayes backpropagation. You know, backpropagation is the general way to train neural networks. Right? In the Bayesian world, we have the Bayes version for backpropagation. Right? And we're gonna talk about the variational autoencoders, which kind of like the most successful techniques in the past decade, right? And the reparameterization trick. How do you conduct the variational inference for Bayes neural networks, right? So if you use reparameterization trick, the implementation will be extremely simple, right? Based on PyTorch or based on TensorFlow, those automatic differentiation libraries. Right? And then general adversarial neural nets. Right? We're going to talk about that. It's a recent techniques. It has a lot of fancy, cool applications. We're going to talk about the ideas of that, how to train them, right? And the Gaussian processes, right? Gaussian processes is kind of a classical topic in machine learning area, but essentially it's a Bayesian model. So we're going to introduce it from the stochastic process view. Right? You see that Gaussian process essentially is a prior over functions. So you might feel a little bit confusing, right? Why we can place priors over functions. But from stochastic process view, a draw of stochastic process is essentially a function. That's why in Bayes nonparametrics, I mean, this is a sub area in Bayesian learning. They always construct different kinds of stochastic processes. And then we'll talk about how to do the computation of Gaussian processes. Gaussian processes have some computational burdens on that. We have to make some sparse approximations. We're going to talk about deep Gaussian processes. Right? If you want to increase the expressivity of Gaussian processes, we want to incorporate deep architectures. How can we do that? Right? But anyway, this is kind of like a tentative coverage, right? Where this based on our time and schedule, we might not be able to cover every points we discussed so far, but the general framework is like that. We're going to talk about the basic concepts as our building bricks, and then we're going to gradually introduce different models and algorithm models and algorithm models and algorithm, and to give you some kind of organized view of this area. Okay, I think This might be the most important part, right? What is the grading policy? So the good thing is that we won't have any final exam, won't have any quizzes or midterm exams. We really don't think this is a good way to check the knowledge. So the final grade is only determined by two parts. One is homework assignments, the other is course project. But the workload is a little bit heavy. It's heavy, but it's not absurd. Right? So we have 6 homework assignments, and homework 0 has been released. Right? So I would suggest you to do that right now in order to check your background and also to review basic knowledge. If you feel good about that, you feel, oh okay, this is easy, or I can just do it very quickly after looking at some books. Right? Maybe you should reference your book, maybe not. If it is easy and comfortable, then I think it's really good. But if you feel very, very hard to do homework 0, and I would suggest you to consider for that. The due of homework 0 will be next Friday, so we have enough time for you to make a decision. So basically, the homework assignments will include both the analytical problems and the programming assignments. Of course, it doesn't include program assignments in homework 0. Homework 0 is just the warm-up questions, right? So the programming assignments usually request you to implement particular probabilistic learning models and test them in real-world or synthetic data sets. Okay. So, and each homework assignment may have a different number of points. It's really depending on the workload, right? But for programming here, we request that you use either MATLAB, Python, or R to finish that. So we do not accept any other programming options. Right? Don't use C, don't use Java, don't use C++. Okay? That's not friendly to do those kind of stuff. For some programming tasks, we may ask you to use PyTorch or TensorFlow, right? Especially when we talk about general diversity networks, Bayesian neural networks. We request everyone to use PyTorch or TensorFlow or other automatic differential libraries. We don't want you to implement everything from scratch, like computing the gradients. So to finish the linear algebra computation and optimization, right, as we emphasize, right, we have a lot of linear algebra computations and also derivations throughout this class. So when you implement your homework problems, we don't want to write a for loop to calculate matrix multiplication. That's not necessary. We request you to use the efficient mature libraries like NumPy, like SciPy libraries to do those things. Right? If you use MATLAB, okay, all the matrix operations, MATLAB R, they have already supported all the matrices and vectors, even tensor operations, right? But you can only use this numerical linear algebra libraries. You cannot use more advanced libraries, like unless we mention that. Like for example, if you are requested to implement a Bayesian linear regression, you have to write down the whole inference, whole model estimation algorithm. You cannot just call one line of code in scikit-learn, right? So in scikit-learn, maybe 2 lines of code, one line of code to create such model, second line of code to learn that model. That's not allowed. Okay. Any question regarding the homework assignments? Okay. So another part of the grade is dependent by the course project. Right? We have 2 types of course project. One is that you can use probabilistic learning techniques, which we introduce in the class, or whatever other places, to address one research or practical problem of your own interest. Like if you're doing research, you want to use some Bayesian learning techniques, so feel free to adopt any probabilistic techniques to address that. That's one way, right? The other is that you can choose 3 recent papers in a probabilistic learning topic. Right? These papers must be published in top machine learning venues like neural NIPS, SML, ASDS, UL, or SAR. SAR is mainly focusing on Bayesian neural nets, not Bayesian neural, but just on neural nets. So you can choose 3 recent papers, read through them, and write down your summary. Right? And for the research project, you need to create a GitHub repository and submit the midterm and final reports. Right? We request you not to write too long report. 6 pages is the limit. And also, the reason we want your GitHub repository is that we want to check if you're really implementing something on that. And for paper reading project, right, you need to submit 1 paper summary before the midterm, and the summaries of the remaining 2 before the final. I mean, final means the end of this semester. Right? And the summary of each paper is at least 2 pages. Right? And that means you cannot use 1 page or 1.5 pages. If your summary is less than 4 pages, you won't have any credit. Right? This is just to ensure that you really understand that paper. Right? And don't copy any sentences or paragraphs from the original paper. If you find that, we cannot give you any point on that. Okay? And we don't have final exam. Okay, I think we should stop here today. I'm sorry for this a little bit lengthy introduction of this course. I just want to emphasize the whole schedule and the prerequisite requirement. Right? So we're gonna continue the discussion on Thursday. Right? See you on Thursday.